Hello everybody. Welcome to the subject electromagnetic waves and transmission lines. In this module we are going to discuss about electromagnetic wave propagation in various medium. Our first application of Maxwell's equations will be in relation to the electromagnetic wave propagation. The existence of electromagnetic waves was predicted by Maxwell's equations was first investigated by Heinrich Hertz. Hertz was succeeded in generating and detecting the radio waves, which are sometimes called as Hertzian waves in his honor. So here let us see the definition for the wave. If a physical phenomenon that occurs at one place at a given time is reproduced at other places at a times, the time delay being proportional to the space separation from first location, then the group of phenomena constitutes a wave. So in general, waves are means of transporting of energy or information from one point to another point. The typical examples of these electromagnetic waves include radio waves, TV signals, radar beams, light rays, etc. So, all forms of the electromagnetic energy share three fundamental characteristics. That is, they all travel at high velocity in traveling, they assume the properties of the waves, and they radiate outward from a source. So, the problem of radiation is going to be addressed in this session. So, our major goal is to solve Maxwell's equations and describe electromagnetic wave motion in the following media. So, actually, the media is characterized by three universal constants, that is, conductivity, permittivity, and permeability of the medium. So, based on the characterization of these universal constants, the media is characterized. See here, lossy dielectrics. When the media is called a lossy dielectric is when the conductivity is zero, permittivity equal to relative permittivity in free space, and mu is written as mu is equal to relative permeability and permeability in free space. For lossless dielectrics, the conductivity is zero, and epsilon is written as usual epsilon r into epsilon naught. Mu is equal to mu r into mu naught r. Lossless dielectrics means omega epsilon is always greater than conductivity. For free space, the conductivity is 0, permittivity is equal to epsilon naught, and mu is equal to mu naught. And for good conductors, the conductivity is infinite. Epsilon is equal to epsilon naught. Mu is equal to mu or mu naught. Or omega epsilon is always less than conductivity. So on this basis, first we derive the wave equation for free space, lossy medium, and conducting medium. So now I'm going to consider a case to derive wave equation for free space. So in order to derive the wave equation, first we have to have some assumptions. First, let us consider the medium to be a linear, homogeneous, and isotropic medium. Linear homogeneous means the quantities permeability, permittivity, and conductivity should be constant throughout the medium. And when you say it is isotropic, that is permittivity is a scalar constant, so that the electric flux density and electric field intensity have everywhere the same direction. And the medium is considered to be a source free region, that is there is no charge in the free space. So we have to derive the wave equations for free space, which takes the form as like this: del square is equal to mu naught epsilon naught dou square E by dou t square, and del square H is equal to mu naught epsilon naught dou square H by dou t square. These are wave equations for free space which we have to derive. For this, we are going to consider a Maxwell's equation, time varying Maxwell's equation. So here, for free space, the relative permittivity and permeability is equal to 1. and permittivity or a dielectric constant of the medium will be equal to free space permittivity. Permeability will be equal to free space permeability, and conductivity is 0, charge density is 0, and the current density is also 0. Because the conductivity is 0, the current density is J equal to sigma into E, so the conductivity is 0. Now, due to these characteristics for the free space, we substitute for these values in the Maxwell's equation, and the 4 Maxwell's equation reduces to these values, and all the Maxwell's equations are written in terms of electric field and magnetic field. You can see del cross H is equal to epsilon dou E by dou T, del cross E is equal to minus mu naught dou H by dou T, del dot E equal to 0, del dot H is equal to 0. These are the Maxwell's equations for free space, where electric flux density is nothing but equal to epsilon E, magnetic flux density is nothing but equal to mu naught H, and current density is equal to sigma into E. Since it is a free space, current density is 0. And the Maxwell's equation, wherever you find electric flux density and magnetic flux density, you are replacing with epsilon naught E and mu naught H. So now, to derive the Maxwell's wave equation, let me take curl on both sides of equation 2. That is curl of E is equal to minus mu naught dou E by dou T. Dou H by dou T, sorry. So, from the second equation, I have taken curl on both sides. So, this becomes curl of E is equal to minus mu naught dou by dou T of curl of H. So, from the equation 1, curl of H is nothing but equal to epsilon naught into dou E by dou T. So, substituting that value here, you get the equation like this. Del curl of E is equal to minus mu naught dou by dou T epsilon naught dou E by dou T. So, that can be written as del cross of del cross E is equal to minus mu naught epsilon naught dou square E by dou T square. You observe here on the right hand side, it is curl of a vector. So according to vector identity, this can be written as curl of a vector is equal to gradient of divergence of the vector minus del square E. So I have using the vector identity, I have written the expression like gradient of divergence of E minus del square E is equal to minus mu naught epsilon naught dou square E by dou T square. But here, according to Maxwell's equation, divergence of D equal to 0, which is not because it's a free space. Actual divergence of D is equal to rho V, right? Charge density. But it's a free space where charge density is 0. So here, the divergence of D is equal to, where D is epsilon naught into E. So divergence of E will be equal to 0 because charge density is 0. Now substituting this value in that expression, we get del square E is equal to minus, sorry, here it's not a minus get cancelled, please correct it. Del square E is equal to mu naught epsilon naught dou square E by dou T square. So this is the wave equation in terms of electric field. And similarly, we can obtain a wave equation in terms of magnetic field by taking curl on both sides of equation 1, that is del cross H is equal to epsilon into dou E by dou T. On simplification, you get on taking curl on that, applying the vector identity where del dot H is equal to 0, and on simplification you get del square H is equal to mu naught epsilon naught dou square H by dou T square. So these are equation 9 and 10, both are the wave equations for free space, which represents their second order partial differential equation. There's second order partial differential equation, homogeneous equation. Okay, these are the two wave equations for free space. So in next session, we are going to discuss about wave equation for conducting medium. Thank you.